let's say I pick this spot here, and then replace that with this one. See that?
Well, what if you replace the first spot?
This one up here?
Yeah.
Then the whole thing gets replaced with that one.
That doesn't seem like a very good mutation.
That's why it's getting all those.
That's why it tries all of
wacky
them.
circles.
Especially that was the closest one. It's like,
But that'll be just one of 100 that it generates.
Oh, okay. So.
But then we clone this one again and try that again. And we clone this one again and do a replacement. Clone this one again. We'll end up with 100 functions that use this as a starting point.
So what you're saying is pretty soon we're going to have PETA on us because we're cloning way too much. There's way too many dead turtles here.
So what I want to do is I want to make a function called replace, or a method. You give it a location number. Sorry guys over there, just this placement here. And a function. This location number is a number. Basically it's some number between 0 and however many nodes there are in this. And then this is the function to hook into that spot. So let's try it on this one here. How many things are there in here? 11? 11? So one possible thing to do is call replace.
1 through what?
Do you mean number between
4?
4? And some random function. Okay, so if we did replace 4 with this random function, and let's say that ends up being this one here, which one are we going to replace? Which one is
Spot
that?
at 4.
Which one's number 4?
The left one. Third down.
How are you numbering them?
1, 2, 3, 4.
Well, first of all, let's start counting from 0.
Okay. 0, 1, 2, 3, 4.
Okay, 0, 1, is that right?
Yeah.
2, 3,
4.
4. Okay, so we'll end up taking this one out and putting that one there. So essentially, the root of this function becomes the thing that was there. So it replaces node number 4 with this one. Okay. What if I did replace 10 with that function? What would happen?
Same thing, but 10 spot.
Which one's number 10?
The bottom left, right one. No.
5.
Yeah.
This is 6?
Yeah.
6, 7, 8, 9. You said it was the bottom right one?
Bottom.
The bottom right.
Very bottom. On the
This
right.
one.
Yeah.
So it's going to replace this one.
Yeah.
Okay. So how do we? So we look at this picture and we call this one number 10. How does that particular node know that it's number 10?
We tell it.
You don't.
So we make another method.
So I'm going to be able to call replace on number 10 and somehow find its way down to node number 10 and then swap out. So how does that node know that it's number 10? So I'm gonna call replace on this one over here. I'm gonna tell node number 0 replace number 10. So what does node number 0 have to do?
Pass on.
It has to pass on the replace. So it has to call replace on
One left and right.
both of them.
No. Just one.
Ideally, number 0 here should know where number 10 is based on the numbering.
Pass to number 1 and number 1 back to number 2. Continue to number 10.
So remember when we were talking about binary trees, and we said that if they were balanced and in order, so if this was number 5, then everything that's less than 5 is to the left, and everything that's more than 5 is to the right. So that way, if I want to find number 2, number 5 here doesn't have to pass along that message to both the left and right. It only has to pass it on to the left because it knows that number 2 is over there.
So we have our number
Well,
system
according-
backwards then.
Yeah,
10
according
should
to
be
that
on top.
tree, that'd be wrong, because if you went to the right, you'd never get to 10.
Or the whole left side is negative.
No, we have our number system wrong.
Because you said 10 is greater than 0 goes to 2, but you'll never get to 10, it just 10's on the left.
Yeah, find it. Oh. Pause for a minute.
Okay, so here's a numbering system that works for this binary tree. Okay, this is a binary tree. This one over here is not strictly a binary tree. There's some places where there's only one thing below it. So this whole left-right thing doesn't necessarily work. Still going?
Yeah.
So anytime you're devising a data structure where the nodes or the data you're storing is in some kind of order, you need to establish a set of properties, also called invariants, that are true for any single one of these nodes. For example, for a strict binary tree like this, every node has the property that it always has 0, 1, or 2 children. Okay, what if you had one that had 3 children? You can say it's not a binary tree. There's something here at 3 children. Another property is, except for the root node, every node has exactly 1 parent. So if you saw a tree that looked like that, you can say that's not a binary tree because there's a node here that has 2 parents.
That tree's from Tennessee.
For a binary tree, you can also say that all the nodes to the left of any given node are less than the node itself. Right? So the numbers stored on each one of these nodes for any given node is always less, the numbers to the left are always less than the number itself, and the numbers to the right are always greater.
That one right there is broken.
Yeah.
3
One.
2.
1, 2, 3.
Oh, shoot, yeah. You're right, so that's not a binary tree. It was true most of the places, but here it was not true, so we can say this is not a binary tree until I fixed it.
So are we getting at serializing these nodes based on their position?
So yeah, we're getting at, can we come up with a numbering system here that is consistent throughout? That we can say that whatever numbering system we come up for this particular node must also hold for all the other nodes. So that we can very quickly determine where a particular node is. We can, for this one over here, we could use those properties to know how to find node number 4. Don't go left or go right. What properties can we do about this one here? I'm going to take away these numbers because you identified they don't work. So that we've got a set of properties that are consistent throughout. And I'm going to throw in one more caveat here to say that a node could have 3 children.
No, it's not that. What's our, do we have a trinary operator?
Yeah, the if else. That's 3. So this is the condition, this is the true branch, and this is the false branch. So we need a way to number these so that we can quickly find a particular node.
Left is less than, to the right is greater than, and down is the same number.
Okay? So what would you start with the first one here? What number would that one be?
8,
Why 8?
just a random number.
No,
Number of nodes divided by 2?
that's why, yeah.
Okay, number of nodes, because each one of these can do a count, right? So we can count, we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 13 in here. So we divide that by 2. 2
37,
6, 7?
7.
Well, you go 13 divided by 2, you're gonna get 6. So let's call this one 6. So, which one is this?
Number of nodes divided by
5,
5 or less?
probably 5.
Number of nodes divided by 2? So if we come up with a property that says that every node is numbered by the number of nodes divided by 2 below it, then this would be node number
3.
1, 2, 3, 4, 5, 6 divided by 2, 3. Okay, or what number is this?
2.
2.
Yep.
1, 2, 3, 4, 2, good.
2.
Big 1.
1. So far so good, we got unique numbers for all of them.
Maybe 0 and a half.
0.
There's 1 here, divided by 2, you get integers. 0. And this one is? 0. So there's 2 numbers 0. So what's this one? 0.
I think when we put the 3,
what's this
we're
one here?
counting the same node.
This one's also 3.
But you have to rate greater than the 6. So on the left is less than 6, but on the right is greater than 6.
Okay,
So it should be 9.
this should be 9. How'd you arrive at 9?
So
Nodes divided by 2 plus the node above you.
yeah.
Number of nodes divided by 2 plus the one, how many are above you? Okay? I'm going to erase them all. That. So, for this top one here, number of nodes below you, which is
6.
13, right?
Yeah.
Divided by 2 is 6 plus what?
Plus 1 on the left side.
Because it's a
Lance?
Oh, well, now it's not going to work.
Why not?
Because you're going to get the same number on both sides again. You had to somehow differentiate the left from the right, saying, you know, do this for the first half, and then the second half, add the add, but don't add for the first half.
This would be plus 6 on the right side.
But how'd you arrive at that 6?
Because that was the 13 divided by 2.
Okay, well, one thing we do is we say the root is special, because it doesn't have anything above it.
that's right.
So we can say this is still 6. So this one is 3,
So close.
right? Because it's the number of nodes divided by 2.
Okay, that one should have worked.
Yeah, it's getting really close. Oh! Oh! Did it get it? Did it get it? Come on. Oh!
Almost, almost.
It finally changed its function.
Getting better.
You're stuck on the same function for a good like 2 minutes.
Yeah.
Yeah, that was.
It'll get it really soon. It's
Okay.
really close.
And this is the number of nodes. We'll see. Lance,
Oh, I think it got it right there.
this
I
is
think you go 6 divided by 2 and then
Uh-huh.
add 6.
add 6. Okay. So what is this one?
9 divided by 2. Add
Oh, I thought it was 1, 2, 3, 4, 5 divided by 2 plus
4.
9.
It's only 4.
Oh, yeah.
Or 5.
1, 2, 3, 4, 5.
Yes, ma'am.
So this is 2 plus 9 is 11. What is this one?
So on the left,
2.
it will be 10.
So it's 11. This one is, well, easy with a problem, right? There's 2 number 11.
Yeah.
All right, so that's not going to work. Do you like this idea where all the nodes to the left have a number that's less than?
No, because you have to recalculate it every time.
That's probably all right.
If you add something, you have to, all your numbers on your nodes change.
That's all right, because we generate a new function, and then we're going to run a replacement on that one, and so of course the numbers are going to change.
What if you did it like the top node is
So use negative numbers?
Well, or you could use 1 and it's halfway to 2 and halfway to 0. The idea being that you use decimals, and then from there, it's always half the distance. It's like the half-life theory.
So, oh, I see. So this is like 0, right?
Right. So then,
This is the midpoint.
then that would be 0.5 and point negative, or negative
This is
0.5.
negative 0.5, and this is positive 0.5.
Right.
And so this one would be
Negative,
Point two.
halfway between
right.
these 2 points. So what would this one be?
Negative 0.75.
And this one?
Was that, so for unaries, you'd have to establish an arbitrary left or right status.
Oh, I see. So even though there's only one thing below it, we can say this is actually the left.
Yeah, you can say it's left.
Okay. So this would be point,
8, negative 0.825 or whatever an eighth is.
875.
875.
So basically, every time you go left or right, you're cutting the distance between
Right,
this node and the one above it in half.
right.
So
And
this-
you're either adding or subtracting.
What do we do about this one?
It could just be all positive numbers?
Yeah.
No, it means there's three children, don't you? That's it.
So this one, we have to cut it in thirds, basically.
Yeah.
Right?
And then for the center one, again, you establish arbitrary right or left status.
Well, if we did left for this one, we should do left for that one.
Okay.
So this would be 0.25.
So then we'll say that in trinaries, the center node is arbitrarily right.
And then
So
what's
it
this
fits
one?
the picture. So that's the right node, so that would be
0.08.
like, what is it,
Point
0.12, or 0.275?
So how are you breaking this up into thirds?
Divide 0.25 by 3. So you're like 0.08, point something,
Yeah,
point
you can
three.
do that. The main idea being that you don't want to end up with a center point that's equal to the node above it.
Right. Well, I think that's I mean, you gotta figure out this 1/3 thing here, but I think that's resolvable.
Honestly, I would divide it by 4 and pick 3 of the 4 values.
So the nice thing about this is that it always comes up with a unique number for every single one of them. Because as you go down, you're cutting the distances smaller and smaller and smaller.
When really, the only limiting factor is how long you can extend your float.
True. Another limiting factor is now, how do I pick a random spot? What number do I put in here for 4?
Random between -1 and 1.
Okay. 0.56821. Where's that node?
So you go right, 0.5,
Uh-huh.
and then it's still greater than 0.5, so it goes right again. Okay. So that spot's not going to exist on that tree,
Yeah.
because it never went right from 0.5.
So what are the chances that I'll be able to pick a random number that occurs in that tree?
Very small.
Very, very small.
So then at that point, you could say if you pick a random number that is outside the bounds of the tree, find the closest node,
Yeah.
which in that case would be the 0.5.
Or you can define on the right side of the tree the unary to go right instead of left.
But then I can just pick another number where the left didn't work. closest one, but then to find the closest one, you know, the closest one might actually be back up the tree a little bit. Because you overshot it here, so you have to go back to find the previous one. And that's kind of tricky to do. Because with the tree, usually you go down, and it's very hard to go back up. The only way to go back up is to return the function and restore the stack to what it was before. So I think that's a good idea, but I think there's like more problems with it. One of them is how do we find a unique identifier that finds a node, and the other is how far can we split these things up until we kind of run out of.
Are we gonna need
That's
to,
Well, if it's doubles, right, doesn't go pretty damn far.
At some point, you start losing precision, though, because a double is still only 64 bits, of which only 20. No. I think you're going to find that it basically limits the depth of your tree to about 40 or so, because you just can't cut it up anymore. You run out of bits.
do you like integers better?
I like integers better.
Still.
It got closer.
It's
We're
getting,
just choosing this at random.
it's getting barely closer. It was
Yeah.
9.3, now it's 9.26.
Yeah.
Yeah, but it
I
just
should
went
prob- I
from
should probably do the fitness as
9.263
not the
to
sum
3.1.
of how close it got, but actually the average of how close it got.
Oh, so Barry,
Yeah.
with the 0, the parent nodes, so if we start there and divide that number by 2, but then before you do anything else, because that's a special one, add a certain amount, then by the time you get down to the bottom,
But what are you thinking there?
because that was, the issue is that when we got to the bottom, we just ended up with two zeros.
Right.
So if you add at the top only, then that would work, because it would leave you with some extra numbers at the bottom.
Well, wouldn't that just go away then once you had more nodes? You just have a new bottom level to get to?
Well,
Yeah,
you're
same
using
problem.
that number anyways to come up with the numerator.
I'm not quite following.
So you have 13 right there,
Right.
divided by 2,
Okay.
you come up with 6, so what if, at that point, you say plus whatever, plus 5.
So we still call this one 6?
No, plus, yeah, well, you say 6 plus 5 or something, so it becomes 11.
Where does the 5 come from?
Just a random number
Oh,
that
just
you
an arbitrary
add to
number?
it, yeah.
So once you start throwing kind of arbitrary numbers into the numbering scheme, then you're back to the problem of how do I pick a number that's out of that tree so that I can identify a spot?
I wanted to ask is, will we actually need to select a specific node, or can we, for this project, is that actually what's desired?
I want to be able to identify, I want to be able to just basically swap one new function in for some spot in here.
And if that spot is selected randomly, then a unique identifier would not be necessarily needed. You might simply ask the first one.
So here's the really big problem. And this is a limitation more of Java than of anything else. Let's say I pick this spot to replace. So I want to hook this into this one here. Whose job is it to do that?
Programs?
Which one of these nodes does that job?
One above it.
One above it.
The one above it. So the thing about Java is an object cannot replace itself with another object. You cannot do, the body of this cannot be like, if my ID equals location, so in other words, if my node number is the one that's been identified as one to be replaced, then do this equals replacement. Okay, what I'm trying to do here is I'm trying to say, take me and replace me with a new function. An object cannot erase itself and make it, turn it into something else. An object cannot commit suicide and replace itself with another object.
But it can't commit suicide.
But it'll be dead, so it can't replace
So it can't,
Right.
yeah, it'll be dead.
So the job of doing the replacement actually belongs to the parent.
So
So
what
the
if
parent
the,
kills it, it's murder. It's murder.
what if the primary function of replace is to return whether or not it is that node? And then the node above it says, if I get a return, then I replace it with this replacement function, right?
Okay.
If I don't, then I don't care, I passed it on and it's out of my hands now. So the only time it'll ever actually replace anything is if the node directly below it returns that it is the node that's being looked for. And then again, it
Okay.
doesn't matter how you number it, because you're just telling the whole tree, look for this guy, the whole tree looks for it, and then,
So that means if I do a replacement, then this guy, the top one here, has to send replacement down this side. And if it got a false back from it, it has to then send it down this side.
right.
So the whole tree needs to be involved in this replacement function. And when we want to do it, this tree could be huge, is so that if we know the replacement is supposed to happen on the left, we can unambiguously say it's going to happen on the left. Otherwise, you just go back and use a linked list for the whole thing. See what I'm saying? So if I ask the left side, do a replacement, and if I get back a false saying no replacement happened, then I gotta send it down the right side.
What if you don't, if I get a false, what if you just send it down both sides?
Well, that's what we're doing essentially, is we can optimize it a little bit and say, well, don't send it down the right side if I did get back something from the left. We could do replace on the left, replace on the right, but then that replace has to filter down through everything. And so everyone gets involved in doing the replacement. So if there's 1,000 nodes in here, all 1,000 get this message to do a replacement, even though only one of them is going to respond to that message. And we want, the whole idea behind using a tree was so that we could just send the replace message down the branch that it needs to go down. So this top person says, if I'm replacing number 4, I know that's down the left-hand branch. I can totally ignore the right-hand one. That's one of the reasons why we're putting in a tree in the first place. So the reason why I can just tell you the solution I came up with, but we need to struggle with this because this is an important problem in doing any kind of let's say you're Google and you want to find out how to get from Sierra College to the Galleria. We need a way to identify where the Galleria is and what its unique identifier is so that we can head our car in the right direction to begin with. Because the way Google does not find the path between here and the Galleria is just send virtual cars down every single road and figure out which one happened to get there.
At what point in time do you stop your
It does this. It doesn't do this. What it does is it says, I know the Galleria is in that direction, so let's start doing paths that start in that direction, and we'll ignore all the ones that go in that direction.
It's getting really close to 5. It's at 6 point something now.
1.5 left.
So we need to come up with a numbering scheme so that every single node knows where the target one is. So it doesn't do this wild goose chase of trying to figure out, well, it could be anywhere. And the other important thing is, it's up to the parent to do the job of the swapping. So the parent needs to know when its child is the one that's going to be swapped out. So we need to come up with a numbering scheme so that we can, first of all, produce a random number that does identify a node somewhere in the tree, and is not hit and miss, and B, tells us exactly where that child is, so I know whether it's on the left side or the right side. So I like this idea of, if this node number is x, then everything that's less than x is to the left, and everything that's greater than x is to the right.
I think the big problem that we're fighting with is that at this point, any given node on the tree only has vision of itself and everything that was above it in the tree. So the parent doesn't actually see its children other than it has pointers pointing at them.
Do you remember how we did find? To tell you whether or not something is in the list, and ultimately where, did we do that here? Contains?
It was part of our homework, but.
Yeah. So over here, like, I want to know whether this tree contains the number 6. So I'll ask the top node. What's the top node going to do?
Move to the right.
String.
It's going to, first of all, am I number 6?
Yeah.
No.
If I'm not number 6, then, well, 6 is bigger than me, so I know it's to the right. So it's going to ask the next one to the right, find number 6. This one's going to go, I'm not number 6. It must be to the left because it's less than me, so it's going to ask the one below it, find number 6. And finally this one goes, oh, that's me. So it returns true, returns true. So two things happened there. First of all, this one here didn't have to ask the left-hand side at all. And secondly, it passed along the message to find number 6 to the one below it. And that one found number 6. So what's going to happen here with replace is we could say replace number 10. And this one here will go, I'm not number 10. But it could go, well, I know number 10 must be to the right. Because maybe it knows it's number 6. So what does it do next?
So it's the message replaced?
It tells one down below it, replace number 10. This one goes, no, that's not me. It must be down here. So it sends this one, replace number 10. But here's the thing. Is this a tree right here? This is a tree, right? And this is a tree. And this is a tree, right? And this is a tree, and this whole thing's a tree. Here's a tree. There's trees all over the place. So if I tell this one here, replace number 10, how does it know where number 10 is?
It doesn't unless it is number 10.
So if it is number 10, everything's cool. But actually, this one should have been doing the job of replacing, because if this is number 10, this is the one that actually has to do the swap. But if all we had was a tree that looks like this, which is just this little piece right here, what node, could this be node number 10?
Yeah. No.
It can't be. There's only 2 nodes in here. And the number starts at 0, and it goes up from there. So one of these has to be 0, and the other one has to be something other than 0. So if we pass down the message to this one, replace number 10, this one's going to go, that's complete nonsense. There's only 2 down here. See what I'm saying?
So we'll have to pass that message to the one on the bottom.
So when we pass the message down, we actually need to change this number. What is number 10 to this one is actually like number 12 or number 4 to this one. And what's number 4 to this one is probably number 2 to that one. Based on the number of nodes that are down below it. And what's number 2 to this one, maybe number 1 to this one, or number 0, and that might be this one down here.
So we're gonna use our.
So we need a numbering system that not only applies for the whole tree, as far as the properties go, but also applies to every single one of the subtrees.
We already have count though.
We do.
So we can.
But so the count for this one is just 1.
I know, but it just needs to know. Never mind. How you just, I don't know what you just said right before, but it doesn't, if 10 is on the top and it's passing down to the next one, it needs to change that number.
Right.
So it needs to change the number to,
Based upon how many things are
yeah, so we
below
need
it.
to do like some kind of subtraction.
Yeah. Okay, so if we have a tree that is just by itself, this is the whole tree, What number is this?
0.
0.
But it's, okay.
Number starts at 0. So if this is 0, this is also 0, but go with me. This is 0, this is 0. From the perspective of this node, this is number 0. From the perspective of this one, this is number 0. Okay, but what about this one?
It would be 1
One.
to the zeros.
But we can't have 2 zeros. So if this is our entire tree, we need to come up with a numbering system so that each one of these has a unique number. One of them is 0, and the other, one of them is 1, and one of them is 2. So what do we pick? So if this is our tree right here, which one is number 0?
The far left,
This one over here?
yeah.
Okay. Which one is this?
2.
2 or 1,
Okay.
depending on which
Yeah,
way it
pick.
goes though.
1.
So we need to come up with a numbering system that is consistent throughout. Okay, so if we say this is 1 and this is
2.
2, good. Then let's go up to the next one here. If this is the root of the tree, what number is this?
0.
This one's 0? Okay. What is this one?
1. Oh, 0.
Now, starting from here, if this is number 0,
Oh,
and
okay.
this is our tree,
Negative 1.
1,
2,
2,
3.
3. Okay, so let's go back to the tree that we had before, which was 0, 1, 2. Okay? Look at these numbers here. Can you come up with any rules about how these numbers work?
They all add.
So if this is number 2, what can number 2 say about the numbers below it?
They're less than it.
They're less than. So if this is number 2, everything below it must be less than 2. When we went up to this one here,
Yeah, they're all greater.
that property doesn't hold anymore. So we need to come up with a numbering system that works for both trees. Now if we change it back to 0, 1, 2, 3, does the property still hold? Where everything below a particular node is less than.
Yeah.
Yeah? So 2 is less than 3, 0 is less than 2, and 1 is less than 2. Okay. So let's say this is our tree. What should the numbering system be?
0, 1, 2, 3, 4, 5.
0, 1, 2, 3,
4 to the right.
4 here,
Yeah.
and 5 here. So does the property still hold?
Yes.
Okay. So let's see if we can number the whole thing then. The whole thing's our tree.